Well, welcome everybody to the last week of our focus program. We continue with a theorem that I mentioned before, but one component was missing, and that is why I couldn't give a complete proof. Now I do it thanks to the hint by Sheldon. So here is the theorem. H and K are RKHS on X, and T, a mapping from H to K, is linear. An important message here is that if you pick any F in H, then T of F is a function in K. That's the meaning of this T from H to K. That's important. But the one which was missing was this one. We also assume that for every X in our ambient set X, the mapping, we don't need to give a name to this, but it's a mapping from H to the complex set of complex number defined by taking F and mapping to TF. And note that TF now is a function in K. So it's a function which defined on X, and we evaluate that function at the point X. The point X is fixed, but for any such point, this mapping is continuous. So if you have a sequence Fn in H, which goes to F, then Tfn at point X goes to Tf at point X. And the conclusion is that then automatically T is a bounded operator. And here is the proof. We use the closed graph theorem. So for that, to use graph theorem, assume that you have a sequence Fn which goes to F in H, and T of Fn goes to G in K. And our goal is to show that T of F is equal to G. And that will imply immediately by the closed graph theorem that T is bounded. And now, based on our assumption, it's kind of immediate to deduce this conclusion, because when we have convergence in norm in RKHS, we have convergence pointwise. So this assumption implies that for every X in X, Tfn at the point X goes to G of X as a sequence of complex numbers. But we had another assumption too. That was the part which was missing, and now it helps us here. This assumption that for every fixed x, this mapping is continuous. I need it here, precisely here. And also, moreover, TFN of x goes to TF of x too. This is by assumption. Continuity of that mapping for every fixed x. And when we put this together, we conclude that g of x is equal to TF of x. And for every x. And so G is equal to TF, and that's the end of the story. So we are done. The special case that we used before, so it's a recall. The special case, H was a subset of K, and we considered the inclusion map, E, H to K, maps F to F. And this is automatically continuous because both properties are satisfied. I mean, if we can, the map we need from H to C is the map which sends F to the image of F, EF, it's not if, it's E of F, at the point X, which is equal to F of X. And we know this is continuous, again, by RKHS, is continuous. And therefore, that important property is satisfied. So, and also the inclusion, really F in H, F is in K2 by this assumption. So the inclusion map is bounded. And now I will use another application of this in more detail, but just let me mention the beginning, then we go into further studies. Our last section of this course is about multipliers, and we discuss a bit about general multipliers, some of their properties, and then more specifically about multipliers in Hardy and Dirichlet spaces. So I'm going to start a session. Multipliers. So H and RKHS is given. A function f, I better call it H. A function h, which is defined on the same set with values in C, is a multiplier of h if for every f in h, when we multiply f by h, it stays in the space. That's the pointwise multiplier, which is simply saying multiplier. There are other types which are equally important, like Hadamard multipliers. There were some talks about them, but that's another story. And the notation that we use here is M of F, sometimes M of H, sorry. Sometimes even more explicitly, we write mult H, because M is used, in particular in the study of Dobrange-Rovniak spaces. M has a meaning, so we avoid to use M of HP, we use mult of HP. That's the collection of all multipliers. Collection of H, a multiplier. We usually work with this set. Sometimes we do a little bit of generalization, and a little bit is here. Instead of assuming that F multiplies the element of H into itself from H to H, we assume that it takes an element from H1 and map it to an element in H2. It's a little bit of general. Sometimes it's useful, and there are some interesting results. For example, the result of I will mention Frickan, and Ross. When we consider different modular spaces, something interesting happens. So a bit of generalization. So we consider H1 and H2 to RKHS, and H is in, now we write mult of H1 and H2, or simply M of H1 and H2, if, or this set is the collection of, for every F is in H1, when we multiply, we obtain an element of H2. So either in this case or in the previous special case, which is important, we can define a mapping, and here is the definition: M index H defined from space H1 to space H2 and maps F into HF. By definition is well defined. I mean, that's hidden in the definition of a multiplier. And clearly it's linear too. So well defined. And linear. But is it bounded? The only thing we need to verify based on our general theorem is that for any fixed x, we look at the mapping from H1, the first space, into the set of complex number, and it maps F into its image, MH of F. That's a function, but that function evaluated at point X. This has to be continuous. But we know what this function is, because MH of F is H times F, and evaluated at point X is H of X, F of X. And the mapping, since H1 is an RKHS, the mapping from H1 to C, which sends F into F of X, is of course continuous. That's maybe our first lemma, or we did in the first week. And then little h of X is just a constant. So therefore, sending F to H of X, F of X is a scalar here. This is continuous too. So we immediately conclude that, and that's an important conclusion, that M index H is a bounded operator. So in other words, if we consider the family of all operators, bounded operators from H1 to H2, in some books they use L of H1 and H2. L of H1 and H2. Some other books they use B for bounded H1 and H2. So the set of multipliers sits here, sits in the set of bounded operators. And we study some properties of this now. To give a structure to the multiplier algebra, I mean, I already slipped from my mouse. Algebra, it's easy to see that it's an algebra, even a unital algebra, because when we consider the constant function 1, so it's a constant function. Then m of 1, multiplication by 1, is the identity element. And it's very straightforward and easy to see that m of f plus or h plus m of h2, it's m of h1 plus h2, so it's these are straightforward. And more importantly, m of h1, m of h2, generally speaking, when you have two operators, say T1 and T2, T1, T2 is not the same as T2, T1. But for the multipliers, it doesn't matter if you multiply by H2 first and then by H1 or vice versa. So this is equal to M of H2, M of H1. And it's the same thing and multiplying by H1 and H2. So that is why we obtain a unital algebra inside B of H1 and H2. And now we want to give a structure to this space. To do so, I recall, strategy that indeed we explored a couple of times, and it was very useful. Probably the most important case that we used this strategy was in the Morse theorem. And it's a very simple idea, but very practical. You have a set A, which has a structure, whatever, for us is an RKHS. It can be a group, it can be a vector space, algebra, whatever structure that we even topological or analytical structure. And then we have another set B, and we succeed to have a bijection between the two. And as soon as we have the bijection, the set B is the same as the set A. We have just, painted its element with another color. So we can transfer this structure, whatever it is, to the other set and put it here. In our case, is an RKHS on a set A. We establish a bijection between another set, and then transfer the Hilbert space, and then the whole RKHS structure to the second setting. And let's see what I mean by this very explicitly. So here is the proposition which explains what I mean. Proposition. H is an RKHS on X with kernel K. That's our first thing. And F here is just a function, from X to C. We do not assume that it's a multiplier now. It's just a function. And you will see immediately why I consider this set H0 is the set of all elements. In the book, the role of H and F, the way I wrote above, is interchanged, but it really doesn't matter. all elements of the space H which are killed by F, means that F times H is equal to 0. So note that this sits in H. And then I defined H1 to be the orthogonal complement of this. So it's H0 perp. So definition up to here. Now put H index F, this is our set, equal to F times H. If F is a multiplier, then this will be a subset of H. But in general, I mean, this proposition is true, even if F is not a multiplier, is another set. And writing H as orthogonal sum of H1 and H0, we see that F times H is equal to F times H0 plus F times H1, but F times H0 is 0. That's the way it is defined. That is why here I can write F H1. So this is the space we consider H index F. And on this set, I do this definition. Put the undefined. Two elements of HF, F H1, F H2, two elements of this. So here I add an index HF. So this is defined to be the inner product of H1 and H2 in our original space H. And H1, H2 here are element of H1. I define it this way. So it sounds to be a bit complicated, but you will immediately see that there is nothing particular about this. It's a realization of what I explained here. You will see more explicitly very soon. But let me finish the theorem. Then here is the conclusion. HF is an RKHS with kernel. With kernel K, let's put F index F here at point X, Y is F of X and K X Y, F of Y bar. That's the end of the set. So I defined a new space, and the new space is HF. And the fact that it's an RKHS is, it should be trivial, very elementary indeed. And here is the reason. Here is the set H. That's the set A that we had above. And we map it to the set HF by multiplying by F. So any element H here is mapped here to element HF. So a function to a function. I cannot immediately apply this simple strategy because what I need here is a bijection. There should be a bijection between the elements of A and the elements of B. So between elements of H and HF, there is no, on general, there is no bijection because maybe there is a collection of elements that all of them are mapped to 0. And this is precisely what I called H0. So now we need to establish out of this a bijection. And the way we did is that this H0 inside H divides or partitions H into some cells, equivalence classes, and we pick one element from each equivalence class, one element. And that is precisely H1. And now between H1 and HF, I mean, between these two, there is a bijection. And as soon as we have a bijection, we can transfer the structure of H1, which is an RKHS, to that of HF. And this is precisely the definition. How do we transfer any structure? You consider two elements here, and you say that the product here is the same as the product of the pre-images here. This is what I wrote here. This is precisely what I wrote here. The product of any two elements is the product of the pre-images. And the choice of H1 and H2 is unique now. That's the reason for introducing H0 and its orthogonal complement. If by chance, in a special case, this H0 is just the set 0, we don't need to do this generality, and we have already a bijection. But I mean, generally we don't have, and we need to do it the way I explained. So up to here it's trivial because of the bijection I explained. The only thing we need to verify is that the kernel is given by this formula. And now let's verify this. So for any y in the space X, and for any H in H1, what can we say about f of y, h of y? Well, f of y is a constant, but for h of y, I can write h and ky in the space h, because that's the reproducing kernel. And now I use the fact that projection is, call it self-adjoint. I mean, P projection onto H1. I simply write it P. I use two properties, P equal to P star, and also the fact that P over H1 is equal to identity. So f of y, h is in H1, so I can write pH and ky h. And transferring P to the other side, I can write it this way. And the good thing about this representation is that now both elements, this one and this one, both of them are in H1. Therefore, I can rewrite the same identity as f at point y, h, p, k. I mean, there is a notation for in the book for P projection of ky on H1. Here they write it ky with a super index 1. So we can write, instead of pky, we can write ky1. It's the same thing, just a different notation. But the important thing here, I can replace H by H1. The main difference here is that H is replaced by H1 here. And why is this good? Because go back to the definition again. Here, when both elements, even it's better here that I write H, or if you wish, H1. When both elements are in H1, that's the definition of the forward image in HF. So I can write this is equal to, still f of y is staying with us, but I can write fh and fky1, but now in the space HF. And note that the two elements here now are elements of HF. So I succeeded to move from a space H1 to a space HF. And it's almost done because I can write this as FH and take f of y inside, fky1 f of y bar in HF, H index. And compare this with what we have at the beginning. That's fh at point y is equal to this, is equal to this representation. And this immediately implies that this is the kernel we were looking for. So the kernel of, I put an F here to show that it's in the space F, HF at point Y is F KY1 FOY bar. Or if you want to bring X also into the picture, it's KYF at point X is F of X KY1 at point X F of Y bar. Another way to write the same thing is that recall K1 was the projection of KY into a space H1. So if I write K2, KY2, the projection into space H0 of the same kernel, then KY is indeed the orthogonal sum of KY1 and KY2. And the interesting thing is that if you multiply both sides by F, then FKY is equal to FKY1 plus FKY2. By the very definition of space H0, this is identically 0. So we obtain FKY is equal to FKY1, and this can be used here. This can be used here. So again, KY in the space HF is equal to F KY. I don't need to put 1 here because they are the same, and F of Y bar. So that's another formula. All these formula are equivalent, but the evaluation of this at the point X is more interesting. KYF evaluated at X is F of X, KYX, FY bar, or more explicitly, capital K. Capital K. I can put F now as an index of X and Y is F of X, capital K X Y, F of Y bar. That's the kernel for that space. The relation between K into both spaces. Here, f of x, f of y bar, kxy, I mean, these are scalars. One might, wonder why I wrote fx, kxy, and then fy bar. Why not fx, fy bar, these two together, and then kxy? Well, as long as we work with scalars, that's okay. There is no problem. But when we go to matrix valued and vector valued functions, then the ordering is important. And that is why the authors here have been careful to keep an ordering which is not important here, but it's important in future. So even though this is true, but better to forget it and write the way they wrote it, because in vector valued, it's important to write f of x first and f of y bar at the end. And now we arrive, using this proposition, we arrive at our main theorem. That's main theorem, say, for multipliers. This is in parallel with a theorem that we had before, which was a crucial theorem. It gives us a criteria to check whether a function is in this space or not. And even up to now, I have used that result several times. Even I will use it today a couple of more times too. That was for the containment of an element in the space. So, but this result is of the same type, but for multipliers. And here is the statement. Well, H1 and H2 are RKHS on space X with kernels K1 and K2. We need to be a little bit careful here. K1 is the kernel of H1, K2 is the kernel of H2. We should not mix them with the K1 and K2, which were in the proof of the previous theorem. In the previous theorem, K1 and K2 are the orthogonal decomposition of one of the kernels with respect to the spaces H0 and H0. But here, K1 is the kernel of H1, K2 is the kernel of H2. And I emphasize on this because later on, I need to decompose K1 according to the recipe we had before. It means that K1 should be written as, say, K11 plus K10 as we had above. So don't mix them up. And here f is a function from x to c, a function. Then the following are equivalent. The following are equivalent. First, f is a multiply from H1 into H2 to a little bit more, but this has been done before indeed. And M of f is a bounded operator. We have seen this before, but still to emphasize is important. And the number 3 That's the essence of theorem. There exists a constant C. This is the constant C, positive, such that f of x, k1 x, y, f of y bar. We know this is a kernel. This kernel is majorized by the kernel k2 with a constant c2. Recall that something like this is not a property, a pointwise property. It means that for any n by n matrix formed with point x1 up x2 up to xn, then you have a matrix on the left side, another matrix on the right side. If you take the difference is a positive operator for any values of n and for any choice of the point x1, x2, and xn. So in a sense, even though it's easy to write this inequality, it's a rather huge restriction on K1, K2, and on F. And moreover, I mean, the important message is the equivalent of 1, 2, and 3. Moreover, we can say a little bit more, about the best constancy here. Normal MF as an operator between H1 and H2 is the least constant, or is the best constant, or the least constant. C, satisfying. Well, let me call this star satisfying star. And the proof of this. Well, that 2 implies 1 is trivial. Indeed, the way in the book it's proved is like this: 1, 2, 3. 2 implies 1, 3 implies 2, and 1 implies 3. I mean, that's the way done in the book. The proof that 2 implies 1 is trivial. And even, I mean, I mentioned here that 1 implies 2, I mean, we saw already. Now let's prove 1 implies 3. As before, we consider the space HF, which is F times H1. That's an RKHS. And we saw in the proposition, and by the proposition, the kernel of this, K, F of X and Y, is equal to, I mean, we saw, but I repeat, K1, X, Y, F, Y. So that's a kernel. And what is our assumption? The assumption, well, 1 is our assumption. Let's look at 1 again. F is a multiplier. It means that F times H1 is in H2. So our assumption. F is in mult H1 and H2 is the same thing as F times H1 is in H2, which is the same thing as, not M, which is the same thing as HF is in H2. And now it's time to use that, that theorem about the inclusion. It's theorem 5.1 in the book, but it was the first theorem of this chapter that we started. Whenever you have two RKHS, one is in another, if and only if, but I just use one direction of this. So by theorem, I add in parentheses theorem 5.1 in the book, inclusion theorem. This is equivalent with the relation constant C, such that K, F, X, and Y is majorized by the kernel of the other one. And we can have a constant here too. And even in that theorem, we saw that the best constant is the norm of the inclusion map. That was a part of theorem 5.1. And so this implies that because we know what is KF, it's written here, KF is this one. So we conclude that f of x, kx, y, and is indeed k1 space h1, fy bar, that's the kernel of hf. This one is majorized by c2, kernel of h2. That's what we wanted to prove. So indeed, 1 implies 3. There is nothing profound in it because the work is already done. The work is theorem 5.1. And finally, why 3 implies 2? No, this is what, well, yes, 1 implies 3, then yes, 2 implies 1, 1 implies 3, and now why 3 implies 2. Again, we can see the HF, which is F times H1, and we know what is its kernel. Indeed, we know that this is true. This is our assumption now. And one more time, we use theorem 5.1, because theorem 5.1, sorry. Theorem 5.1 says that, let me go a little bit up. If you have this inclusion, then you have this this relation between the kernels. You have this, either this or this, they are the same. And this is even only if, I mean, from this, you can also go back to this one. That's theorem 5.1. So I use that theorem again, saying that this property implies that, so implies that h of f, so by 5.1, h of f is a subset of h2, which implies that f h1 is a subset of h2. And now let's decompose h1 as we did above. I mean, I write H1 is equal to H10 plus H11. H10 is the part which is killed by F. I mean, F H10 is equal to 0. And H11 is the orthogonal complement of that. So, and H11 is H10 perp. And so every element of H can be written as H0 and H1 in these spaces. When this is in H10, this is in H11. And now what can we say about, let me go a little bit up. What can we say about the norm of F H2? No, norm of F in H2. What can we say about this? Well, first thing is that FH is FH0 plus FH1, but the first one is 0, is just FH1. So the norm of FH is the same as the norm of FH1. And this is less than or equal to the constant, the same constant which is above between the kernels, the norm of FH1 in a space HF. That is coming from this assumption, from this one. And the fact that when HF is in H2, the inclusion map is continuous, and the norm of the inclusion map is at most C. The best constant here is the inclusion map. So that is why I have C here. And now I can write here C. And you see now why I did the decomposition. Because now I can write this is equal to C, the norm of H1 in H11. If I keep H here, it's true. I mean, I can do the inequality and I arrive here at FH in H of F. It's true, but I cannot write this is equal to the norm of H in H1. This is not true. That is why I did this decomposition. But at the end of the day, it really doesn't matter because we are interested in less than or equal, and orthogonal decomposition, norm of H squared is norm of H0 squared plus norm of H1 squared. So here I can write is less than C norm of H in H squared, in H1, sorry. So even though this is not true, but still I arrive at the same conclusion that I wanted. And so this implies that M of F is bounded. So this implies that M of F is bounded. That's by comparing this part.
Sir,
yeah.
It will be without square.
I'm sorry?
There will not be square. It will be just knowledge.
I don't hear you well. I mean, the line is cut.
Am I audible?
Hello?
Hello, am I audible now?
I hardly hear you. Do you have a question or comment? Okay, let me see the chat. There will not here. There is no square. And indeed, that is why, let me go back here. That is why a square is here. The square is here because if you don't put square, then here you have to write root square of C. And if you mean this one, yes, you're right. I have to remove that. Sorry, maybe you meant this one. There will not be squared. Maybe you meant this. Yeah, you're right. So if I compare this with this precisely means that MF is bounded and also a restriction on its norm, and the norm is, and the norm of MF is bounded by C. To finish and have a break, we can take M of F to be C and start from this. Indeed, if we take, and so this is done, if we take the constant to be C, then for any H1 is in H11, we can write norm of F H1 in H2 is less than or equal to the norm of MF, norm of H1 in H1. And which is equal to the norm of MF, the norm of F H1 in the space MF. And this inequality, again by the same theorem I mentioned before several times, implies this box formula with C precisely equal to the norm of F. So this implies f of x k 1x and y f of y bar is less than or equal norm of MF squared k2 x and y. And that is why I said the best constant, the least constant is norm of F. That's the end of the proof. I went a little bit over time. I apologize for that. Just wanted to finish this. So maybe we take a break and then come back. Let me see, there is something in the chat. Yes, okay, thank you. So